Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video I'm going to talk about continuity. I'm actually going to be starting the topic of calculus, and specifically I'm going to be talking about what a derivative is. And in order to define a derivative properly, I have to talk about the concept of limits. And in order to talk about limits properly, I have to talk about continuity. So this video is continuity, the next video will be limits, and in the next video after that, we will actually start differential calculus. So the idea of continuity is fairly straightforward in the context we're going to look at it. If you think about it in terms of drawing the graph, if you can draw the graph of the function without lifting the pencil, it's continuous. If you have to lift the pencil and put it somewhere else to continue drawing, it's not continuous. So the formal definition is a function is continuous at a point if two conditions need to be met. First of all, the function is defined at the point. So it exists at that point. So that's the first condition. The second condition required is that if you make a small change in the independent variable, and often you probably relate the independent variable to x. So x is the most common independent variable that we have been working with. So if a small change in x or that independent variable will create just a very small change in the dependent variable, or typically y, or it could be called the function. A small change in the independent variable will result in a corresponding small change in the dependent variable or the function or y. So we're going to take a look at some examples to see where a function is continuous or where it is not continuous. And we would say a function is continuous over an interval if it's continuous at all points in the interval. So let's take a look at some graphs where I can explain this a little bit better. In my first example, I have the graph of some function, f of x. And the question is, was I able to draw that graph without lifting my pen or my pencil? Yes, I was. Are there any breaks in that graph? No, there are no breaks. Therefore, we would say that this function is continuous for all values of the independent variable. In this case, we're calling the independent variable x. The independent variable will always be along the horizontal axis. Your dependent variable is the vertical axis. And I did talk about independent and dependent variables when I talked about functions and domains and ranges. So you might need to go back and take a look at those videos first. We would say this is continuous for all values of x. In my second example, I would ask the same questions. Was I able to draw the graph of this without lifting my pencil? No, I had to lift my marker to make that. By the way, this open circle here means that the function is not defined at that point. Again, I talked about that concept when I talked about set and interval notation in a previous video. But the open circle means that it doesn't exist at that point. A closed circle means it's defined at that point. So that means that our function is not defined when x equals 1. Our first condition for continuity says it has to exist or be defined at that point. So this is not defined. When x is equal to 1. So we would say continuous for all values except of x. We would say it's continuous for x not equal to 1. So it's not continuous when x equals 1. It's continuous up to that point and it's continuous after that point, but it's not continuous at x equals 1. So when we say continuous for x not equal to 1, it means it's continuous for all values except that value. So our first condition of continuity is not met. It's not defined at that point. This third example has what's called a piecewise function. It's defined differently for different intervals. So it's defined as this graph or this shape for values of x less than 1. It's not, there's an open circle, so it's not defined as that shape or that function when x is equal to 1. However, at x equals 1, here's a closed circle, and for values greater than that, we have it defined as this function when x is greater than or equal to 1. So the question is, did I have to lift my pencil or my marker? Yes, I did, to draw this. The first condition is met. This piecewise function is defined when x equals 1. It's defined as this value, whatever that y value is. But the second condition isn't met. When I have a small change, let's say I'm at 0.99999 and I move to x equals 1, there's a big jump in the y value. So the second condition is not met in this example. It's defined, so the first condition's met, but there's a big jump. This one's not continuous because it's not defined. So we would say continuous for, again, x not equal to 1. Now the idea of continuity is going to be important when we find limits, and that's going to be the next video, but I just want to sort of introduce you to the idea first. When you're finding a limit, you're finding the value that the function is approaching as your independent variable approaches another number. So let's take a look at 1. And let's put a y value here of 2. And let's put a y value here of 3 and a y value here of 1. So if I looked at this graph and I said, what is the function approaching as x approaches 1? Oops, let's put our y value here as -1. So if I wanted to know what value the function is approaching as x approaches a certain value, let's say 1, I can see that this y value is -1. So we can see as x gets closer and closer to 1, y is getting closer and closer to -1. And that would be true if we approached 1 from the right-hand side as well as the left-hand side. So that's what the idea of limits is. We would say the limit of this function when x is approaching 1 would be -1. If we took a look at this second example, and I said, what's the limit of this function as x approaches 1? Or in other words, what value is the function approaching as x approaches 1? We can see as we get closer to x equaling 1, it's approaching a value of 2, and it's doing it from both sides. So even though the function isn't continuous at that point, we can still find a limit at that point. And the limit would be 2. In this example, if I said, what is the limit as x approaches 1? Or in other words, what's the function value approaching as x approaches 1? We can see it's approaching 1 as we approach it from the left. However, if we approach 1 from the right, it is approaching a y value of 3. So in this case, we would say a limit doesn't exist. There's only one-sided limits. And for a limit to exist, it has to approach the same value from both sides. So that just gives you a little hint of what we're going to be talking about in the next video. Okay, take care, and we'll see you.